All right, let's talk about it.
I feel very confident. I was
Good.
and I got
The answers are on the board, not the tables, but the graphs and the equations. Are there any of these that we want to ask a question about? Pay attention to the details to make sure that you have the graph matched with the correct equation.
Oh, I think we got 3x.
I'll make sure it's right on mine.
I think I just swapped these two. Yeah, I've been taking them together like that.
All right. Do we have any questions about these graphs and these equations? Kyla, LaShannon, Jada, do y'all have any questions about these graphs and equations?
Yeah, we still doing them.
Well, we have to go over them. We got to move. Which one are you stuck on?
We're not stuck on.
Okay, but check the answers that you do have. So, really quickly, I need to cover this because this was frustrating, and maybe it was frustrating for the wrong reason, but this is something in Algebra 2 we should not have a question about. And I am sorry that I got frustrated with you, Jada. I know that was not your favorite thing. But y'all, if you have an equation, I need you to pay attention to this very clearly. If you have an equation, f of x equals 1.5 raised to the x, and I tell you, or you have the option that x is -1, what's the only thing you have to do to figure out what the y value is? Plug in -1. That's all you have to do. Y'all are making that way harder than it has to be, because all we need to do is substitute that -1 in, and what did we get in the calculator? 2/3. I believe most of us would have gotten 0.6 repeating, but there's a way to use the calculator to convert that to a fraction, and it does become 2/3. Then you substitute a 0 in. And what's 1.5 raised to the 0? 1. And then what is 1.5 raised to the first?
1.5.
Okay, I want to point this out because way too many of us were having to use a calculator on these things. What is anything raised to the 0?
1.
Look at all your tables. Everything raised to the 0 is always what? 1. Does anybody remember why that is the case? So, if you have 3 to the second, most of us are just used to saying 3 times 3, correct? And we say 3 to the first would just be 3. But then it doesn't really explain 3 to the 0 very well, ladies, and I want you to pay attention to this because this will help you significantly. It's not just 3 times 3 or just a 3. It's technically 1 times 2 3s. Then 3 to the first is 1 times 1 3. So then 3 raised to the 0 is still a 1, but how many 3's am I multiplying by? None, which is why 3 to the 0 is 1. For a similar reason, 3 to the -1, I still started a 1, but what am I doing instead of multiplying? Dividing by what? 3. For the same reason, 3 to the -2 would be 1, and then divided by 3 times 3. You've got to know that. You've got to understand how those exponents work. Now, we need to focus on this, right? Part number 2, part A. What point do the graphs all have in common?
Every 0.
They all have what point?
1.
That's not a point.
0,
0, 1. Why does every exponential function in this setup have that point 0, 1? LaShannon, Kyla, Jada, you can tape stuff in a second. I need y'all focusing on this conversation.
Anything.
Oh, hold on a second. Sorry, I just realized something. Most of us don't have our textbook out, do we? This is in the textbook. We need to be writing this down, so go ahead and, it is on page M3-108. So remember, this is volume 2. Does anybody not have their volume 2 with them? M3-108. Who needed? Anybody else? Y'all have it? Who over here needs it? Jaden? Okay. Huh? So, M3-108, or it's in the textbook, or it's on the sheet that I just gave you. So what point do the graphs have in common? They all have 0, 1. And why is that? Any number raised to the 0 power is 1. Any number raised to the 0 power is 1. That's always going to be true. Does anybody know a way that we could algebraically write that to show any number being raised to the 0 power? What do I have to use to indicate that it could be any number? A variable. Does anybody remember which variable we usually use to represent the base of an exponential? B. B for base. Right? So any number, the base, raised to what power? 0 is equal to 1. That's algebraically what we would write to represent that same exact idea. Okay? Now, this is an important distinguishing factor. We were already able to tell from the graphs when it was growth or decay, because you always read from left to right, and if it was growth, the function was what? Okay, what's the mathematical term for going up? Increasing. Remember how we had domain intervals of increasing and domain intervals of decreasing? So for an exponential growth, it is always what? Increasing. Well, Shannon, you go with that? You sure? Why are you frustrated? That's a whole lie. You understand that you're saying going up, but it's increasing. Like that's. So what's wrong? Okay, never mind. So then a decay function will be always what? Decreasing. Growth increases, decay decreases. But what we want to look at is equation-wise, right? We saw the graphs equation-wise. When was it always increasing? Does anyone see a pattern?
Is this, wait, can you say that question again?
Is there a pattern for the equations when the function exponent is always growing? And I'm going to let LaShannon answer first because she did start first. And then we'll go to Cameron since you thought you had an idea.
I don't know when the X is higher. And then
When the what is higher?
when the X is
Higher than what?
higher.
So remember, I mean, x is x. We're talking about the equation right now. Does that x ever change? But look at the equation. Just looking at this equation, does that x ever change? No. Say again. It's just the variable. And so like a variable within the function can change, but what I'm looking at is across these functions, when is the function of growth, when is the function of decay?
You asking me what is the, okay, so the function of growth is when it starts to increase. If you look at it left and right,
But are you looking at the equation or are you looking at the graph?
look at the graph.
Okay, but I'm asking about the equation.
Well, it starts going down when the numbers go down.
Okay, but you're looking at which representation are you now looking at?
The equation.
But what representation am I asking you to look at?
Let me look at the equation. You said
Right.
that
But you keep focusing on the graph or on the table. We are focusing on the equation. There is a pattern. And I'm not saying you have to know this off the top of your head. I'm saying that there is a pattern if you look at the equation and pair it with our understanding of the graph. Cameron, what were you thinking?
When it's growth, it's like over one,
What is over 1?
like, the function, I guess you would say. Like, on the decay, it's like a fraction or a decimal, like a part of a, I guess under one.
This is a decimal. Is that a decay?
Or meaning, like,
the
But
higher,
it's over one.
if it's increasing, the numbers get higher, and if it's decreasing, the numbers are lower, in the equation. I guess I can-
But higher or lower than what? And you're close, but you're missing a key word. You keep saying it. If you're using the word it, you're not being precise with your language. What needs to be greater than 1?
Is that a
The
variable?
base,
Variable.
the base,
Say that one more time.
the base.
The base. Isn't that the base of our exponential function? So the exponential function is a growth when the base
Just have
is greater than 1. How could I mathematically represent the idea that the base is greater than 1?
that thing.
That thing? Okay, but what do I need on the left-hand side? So 1 is greater?
No, B.
B, the base, is greater than
One.
1. That's algebraically how we would represent the idea that the base is greater than 1. So it's an exponential the exponential function is a growth when the base is greater than 1. Let's check that. Here's a base greater than 1, a base greater than 1, and a base greater than 1. Do all of those graphs and those tables show exponential growth? Okay. It's an exponential growth when the base is greater than 1. So then it's an exponential decay when?
The base is lower than 1.
It's base.
Say that. Or less than.
So the exponential function is a decay when the base is less than 1. You think it's always when it's less than 1? Are there any numbers that might be problematic? 0?
1.
Equal.
Well, it's already less than 1, right? We already said less than 1, so 1 would be problematic, but what about 0?
But that's less than 1.
Correct, and so that's the thing to think about. F of x is equal to 0 raised to the x. What's 0 to any power? You're thinking about raised to a 0, but if it's 0 to a power, that's always going to be 0. So can the base be 0? Actually, you can't even do negative exponents. We'll talk about why later. Technically, 0 raised to the 0 is undefined. 0 to the 1 is 0. 0 to the 2 is 0. 0 to the third is 0. Is that an exponential decay? Why not? Saying the same, meaning it's not what? There we go. Remember, if it's a decay, it's got to decrease, right? Is this decreasing? No. So, we can't have a 0. So we already said we can't have 1, we can't have 0. Is there anything else we can't have? Okay, infinity, I'd agree. What about a negative 2? So you can do negative 2 raised to, well, hold on one second. So type in negative 2 raised to the negative 1 in your calculator. Make sure you put the parentheses in there because the base is negative. It's not a negative 2 raised to the x. Jaden helps pick up the calculator. Raised to the negative 1 for now. So negative 1 half. What's negative 2 raised to the 0?
No.
Remember your parentheses. So 1.
No.
What's negative 2 raised to the first? And then negative 2 to the second? Tell me, is that growth, or is it decay, or is it neither?
Neither.
Why is it neither?
Well, it's because you keep going up and down.
So notice it goes up and down because it goes from a negative to a positive to a... So is it growth or decay or neither?
Neither.
Neither, right? So we can't have... It's not just that the base is less than 1, it's got to be less than 1 but greater than...
0.
Say it one more time. 0, right? The base has to be less than 1 but greater than 0. Okay? And so mathematically we would say that as 0 is less than b is less than 1. Notice how that's putting the base between 0 and 1. You can also flip it and say 1 is greater than b is greater than 0. Just b has to be between 0 and 1. Oh wait,
Did you print it out?
no, but yeah, I gave it to her.
Oh, okay. I was just
Remember you were supposed to have volume 2 today.
Well, I got it in here, I think. I got one.
Okay.
I just keep them in my backpack.
Well, you won't need volume 1 after today, you'll just need volume 2. Okay. Any questions about that before I move on? Any of those ideas? Cameron, you good?
Yeah.
Grayson,
Sorry.
good?
Yes, sir.
Jaden? Nathan? Jada? So you're straight? Okay. So here's activity 2.1 that's on the back of the page you were just looking at. Looking at number 1, we've actually already answered most of this, so we're going to move through this pretty quickly. Sarah and Scott's teacher asked them to each write a rule that determines whether a function represents exponential growth or decay based on its equation. Sarah said for exponential growth functions, b is a value greater than 1, but for exponential decay functions, b is a fraction or decimal between 0 and 1. Scott said for exponential growth functions, b is greater than 1, for exponential decay functions, b is less than 1. Work with your small group to come up with an answer for why is Scott's reasoning incorrect, providing a counterexample that would disprove his claim and explain your reasoning. And then number 2, which b values for the function f of x equals b raised to the x produce neither growth nor decay. We should already have some notes about this, should not take us long. I'll be coming around, please talk with me or throw up your hand if you're completely confused, but let's talk with our groups and get this knocked out ASAP.
Sarah,
Come on, talk with each other.
No, that's what
Yeah, the 0 would be included, right? In the, what's the? Like, I'm gonna be Scott and Scott.
well, that's basically what we
You
just
should have notes on the previous page that you can basically just copy
said. No,
down.
I know, but.
Okay. Just your brain hurts in general.
That's the first time I understand it. Well, it is in 0.
We had to move on from stuff.
So we're.
Huh?
And she's right.
The first part of it is significantly easier, yes. The later part's not harder, but it is completely easier.
It's not zero, it has to be in between zero.
Oh, well, cause it is, B is, B
okay,
can
like
be greater
like
than
decimal.
one, but
Yeah.
B is.
So,
It says Scott's is wrong.
The only thing she's missing is it has to be greater than 0, because when we did it up there, it didn't increase it.
And remember, did we have those negative bases? So that's an important distinguishing factor.
Yeah.
Okay, we do have to take a
She's
look
right there.
earlier.
Sorry.
Oh, no, that's not like, we have to write something that makes his argument wrong.
We'll just explain why the argument is
I
wrong.
didn't think you actually listened.
Oh,
Writing down word for word. Scott is wrong because he only says it has.
That's my
Everything was
Sure.
Zero, I mean,
Yeah, 0 and then
negatives.
negatives.
Zero.
What'd you put on there? Just.
I just get a lot of motion, two, and then.
That's a great word for it too. So remember, that's what we did up there with the negative base, how it alternated between being a -1/2 and then a 0, and then a -2, and then a +4. So it's neither growing nor decaying.
I just rewrote it. Oh, I just put 0 and negative, and then
Okay, so what was Scott missing?
But greater than 0.
Okay, so B has to be greater than 0 as well, right? It has to be a number between 0 and 1. And that was a great part that Sarah had included in here. So, which B values produce neither growth nor decay?
Negatives and 0.
So, negatives and 0. So, how can I write that as a single statement that it's all negative numbers and 0?
Less than or equal to 0.
If something is less than or equal to 0, right, that's the 0 and it's got my negatives, so what needs to be on the left-hand side here? The B, right, the base. If the base is less than or equal to 0. Is there any other number that we have not talked as heavily about, it's come up a couple times, but is there any other number that would not produce a growth or a decay? Well, infinity's not necessarily a number, but remember, actually a decimal follows, certain decimals fall between 0 and 1, so that would be a decay. And if it's greater than 1, it's a growth.
Pi?
Well, is pi greater than 1 or between 0 and 1?
Pi.
Still greater than 1. Okay, I want you to remember, for it to be a decay, we said it has to be 0 is less than the base is less than 1. For a growth, we said that the base has to be greater than what?
1.
So what number is not ever equaled? 1. I did not hear you say that. Because think about it. If I have f of x equals 1 raised to the x, what is 1 to the second? What is, so f
So
of
it'll
2.
never go up, it'll just be 1.
Right, even if it was negative, f of -3, that would also be a 1. What's 1 raised to the 0? 1, right? And so we want to recognize that the base of 1 also would not produce a growth or a decay. It has to be greater than 1 or between 0 and 1. Any questions from there? Okay. So, couple of quick things on this one. I want you to notice that this is, y'all don't have this page if you don't have the textbook. Hold on, I got it printed out for you. This is yours, right? No. Y'all all have it. Who needs it here? Huh? No, that's for you to study from. There you go. Okay. Really quickly, because this will help us understand our different ideas a little bit better, or some ideas a little bit better. So write an exponential function that satisfies the given characteristics. First off, if I were to tell you, hey, this function increases over negative infinity to infinity, right? That's my domain interval of increasing. What do you know about this function? Think about the graphs and the functions we just looked at. You're thinking of polynomials. Remember, we're on exponentials now. Think about the two different types of exponentials we just focused on. Think about those graphs that you tape to your organizer. What type of function would increase from negative infinity to infinity?
What you mean?
Oh,
So, the exponential functions we just looked at,
Yeah.
you had 6 of them, 3 grows, 3 decays.
You asking me what?
I'm asking you which type of function would increase from negative infinity to infinity?
The growth
Grayson and DJ are thinking growths. Anybody want to push back on that, or do we all agree?
Yeah, no. I agree.
You do?
I don't feel like I should agree with it.
You feel like you should or should not?
I don't know. Yeah,
Okay.
Because it's starting off a negative, but it's going to a positive, so that's increasing, right?
Be careful. So, an exponential growth looks like this. You say it starts out at a negative. Negative what?
Infinity. It's,
Are you talking about the x or are you talking about the y though?
I'm talking the x start off with negative infinity, and then the y goes up to positive infinity. So,
But you just mixed x with y. Right? You're talking about the y is going up to positive infinity.
yeah.
I agree.
The x is starting off with negative infinity.
But you're mixing your x and your y. What does the y start out at?
Positive infinity.
No, it doesn't.
it starts out at negative. No, it starts at
Well,
whatever down there.
it goes x and y.
I mean, it's also
So, let's talk about one key term that we are, I think, missing. First off, do not mix your x and your y's. When we say it's increasing, remember, we're already saying that the x minimum is negative infinity and that the x maximum is positive infinity. That's referring to the left and the right. But to say that it's increasing is saying that what is increasing?
The other x increasing.
X always increases because you always read a graph from left to right. That's what I'm saying. We're giving the interval over which it's increasing. So, what am I saying is increasing? The y. So what is the y value starting at?
A negative.
Say that one more time, DJ. 0. This right here is known as an asymptote. Okay? This is a keyword on your graphic organizer. An asymptote is a function that a graph approaches at as x is a function that a graph approaches at one of the end behaviors, let's say it that way. An asymptote is a function that a graph approaches at one of the end behaviors.
This is on for exponential, not that L word.
Logarithm, correct. Right, because we're only looking at exponential functions right now. But I will say, let me say it this way. This is the definition of an asymptote. The asymptotes are written differently for exponential versus logarithm. And you'll see why when we get into logarithms. But an asymptote is a function that a graph approaches at one of its end behaviors. And LaShannon, here's how we should know, and this is something you all need to pay attention to. I'm only saying LaShannon because she was the one who was talking about negative infinity earlier. An exponential function can never become negative infinity in the y unless there's something called a reflection. And here's why. Y is equal to 2 to the x. Okay? If I have a negative exponent, what is that negative exponent going to tell me to do?
Yeah,
Remember, a positive exponent is repeated
nothing.
multiplication, and negative exponent is repeated division. Is that going to be a negative number?
No.
No, that's a positive divided by a positive. It doesn't matter if the exponent is negative. The negative exponent is always going to give me a positive number. But if I take the number 1 and I divide it by 2 raised to the 100, what's it going to get close to? 0. Okay? So there is a horizontal asymptote. And I want you to notice, is it the x or the y value that's becoming 0? DJ seems to think the y value. I'm going to get a lot of blank looks from others, or no looks at all. CD, you looking at this?
Well, don't the x start off at 0? You said the x starts at 0.
Does this x start at 0? That arrow is going to keep going to the left, doesn't it?
Yeah.
So what's that x going towards?
It's at 0.
That x is going to negative infinity. Also, look right here. What is equal to basically 0? Y. This is a y value.
So the
Of
y is
0.
equal to 0.
So the horizontal asymptote here would be that y is equal to 0. And that is important to notice. You can look at the graph and make sense out of this as well, because here's a y value of 1, here's an x value of or y value of negative 1. What's in between negative 1 and 1? 0. So it doesn't matter what point I'm looking at.